Hello, welcome back. At the end of our last video, I was talking about points where the potential is zero. So these are points where the potential is the same. So moving on from that, you have entire surfaces where the potential would be the same. So this was a two-dimensional viewpoint of this, but what if it was really more like a circle that goes around? Think in 3 dimensions, right? There's a point somewhere out, if there's a line, there's a point somewhere out here or somewhere over here where I'm also twice as far from this point as I am from this point. It's not just 2 points, it's actually more. It's 2 points on that line, but if I go into multiple other dimensions, there are more points where it's the same potential. And we call those equipotential surfaces. It's a surface in which the electrical potential is the same everywhere. And much like with gravitational potential energy, if I stay the same height from the ground, I do no work because I've not changed your energy. Well, if you move along an equipotential surface, you do no work because you haven't changed the potential energy, right? The kq over r stays constant. So the electric field created by any charge or group of charges is, so that's just knowing an equipotential surface. How does that relate to the electric field? All right, so here is a point charge, and the electric field created by any charge or group of charges is everywhere perpendicular to the equipotential surface. Now remember when we were talking about the rules of uh, electric field lines. So that was last chapter. So we already have rules of, so let's pretend that these red lines are electric field lines. Not pretend, that's what they are. Much like the electric field lines are perpendicular to the charge from which they come, the electric equipotential surface is also perpendicular to the electric field line at all points. So that's kind of a rule to creating electrical equipotential surfaces. So equipotential surfaces are related to the electric field lines in that they are perpendicular at all points. So that leads me to this kind of drawing here. I have a positive point charge and a negative point charge, and the red lines represent the electric field lines. They're the same, the magnitude of the charges is the same. And what I want you to notice is the blue lines represent equipotential surfaces. So right down the middle would be an equipotential surface of 0, where they are both, where it's the same distance from both, right? I don't know how to put it otherwise. It's the same distance from both. Everywhere along these lines, you'll see the equipotential surface lines where the potential is the same everywhere on that line. And don't think of them in just in 2 dimensions, it's actually 3 dimensions, is the same. Everywhere perpendicular to the electric field lines. So you have surfaces of where the potential is the same, not just points where the potential is the same. And these drawings help represent that. All right, so that's equipotential surfaces. What if I do it in terms of like a parallel plate capacitor? The plates of a parallel plate capacitor are equipotential surfaces. That's what they are. They're an equipotential surface. The surfaces shown between the plates are also equipotential surfaces that are parallel to the plates and perpendicular to the electric field. So the electric field goes from positive to negative. So everywhere between, every sheet between those two will also be an equipotential surface because it'll be the same distance from each plate no matter where I put it. Not meaning that it's the same distance from positive and negative, but everywhere along this plate is the same distance from positive. And everywhere along this plate is also, although it's a different distance, it's the same distance from the negative plate. So that makes all of these equipotential surfaces as well. And therefore, within a capacitor, you can actually determine the electric field ends up being equal to the change in voltage as you go a certain distance. So the delta, the change in voltage divided by the change in distance will tell you what the electric field strength is. Because, yeah, I mean, voltage is basically related to the electric field strength times the distance that it moves, ES, right? So if I take EPE, which is Q naught ES, and I divide it by Q naught, I get ES. So it's just this same equation. That's just voltage is equal to ES, only with a negative thrown in because of, how do I say that? Well, because this is the actual value and this is a delta, so it's a change. So that volt per distance is called potential gradient. So that's volts per meter. And it's basically a way that we look at parallel plate capacitors. Now, I'm not going to talk much about parallel plate capacitors just because we don't have time, but I just want you to kind of understand that all of this ties in. But let's look at an example. The plates of this capacitor are separated by a distance of 0.032 meters, and the potential difference between them is negative 64 volts. Between the two equipotential surfaces, shown in color, there is a potential difference of negative 3.0 volts. So you have these two plates, and I know the distance between the two plates, delta S, is 0.032 meters. I know the potential difference over that entire 0.032 meters is negative 64 volts. If I put two other plates, two other equipotential surfaces in there, the difference between those two surfaces is negative 3 volts. How far are they apart? Well, if the total is negative 64 volts, the volt per distance, 64 divided by 0.032, is 2.0 times 10 to the third volts per meter. So if I want to find if I know that and that's if it's a 64, if I want to know what the distance is with a delta V of 3 volts, I can use that E that I just solved for and see that it is 1.5 times 10 to the negative 3 meters. So first you solve for the E, and then you, knowing the full delta S, and then when I don't know what the delta S is, all of these ratios still, it's like the ideal gas law. Everything stays the same. If you change one, you have to change something else. In this case, I changed volts. So since I changed volts, the delta S also has to change. You could do this with ratios also. There are other ways of doing this problem. Okay. I'm just looking at this, wondering if we're going to have time to get to it this year. And we'll at least have time to get to, you should at least know what a dielectric is. Let's say that I have a parallel plate capacitor, two metal plates. It is very common to fill these parallel plate capacitors with an electrically insulating substance called a dielectric. It basically maintains the plate's separation. And if that's true, then I can actually, I can actually transfer electrons from the negative plate to the positive plate, and it's easier to basically generate electric flow that way. Now, the magnitude of the charge in each place of the capacitor is directly proportional to the magnitude of the potential difference between the plates. So if I have two plates, we get this thing called capacitance. And capacitance is basically the how do I want to explain this? It has to do with, I mean, really the units, I guess, explain it. How much coulombic charge you have per volt of potential difference. And we call that a farad after Faraday. And you'll actually see that on the capacitors, and we'll actually see that in the lab that we did in the last chapter where you saw the little capacitor. So it's basically related to how much charge it can acquire. All right, so the magnitude of the charge Q is equal to the capacitance times the volt, or capacitance is charge per unit per volts. So C is equal to Q over V. Q is equal to CV. I'm just going through this to see if we're going to have time to get to any of this stuff, because I don't think we're going to have time to get that much into capacitors this year. If you're interested in what capacitance is, you can look over that section. But I do want to at least go over to this part, this last thing on energy. The energy that you can store in a capacitor, which is kind of like a more interesting thing. The energy that you can, so I'm trying not to, I didn't mean to move it there. The energy that you can store in a capacitor. So if somebody asked you if you knew what the capacitance was and you knew what the voltage difference was, the energy that you can store is equal to 1/2 the capacitance times V squared. So this 1/2 CV squared, I didn't go into deriving it because I skipped all that, but I do want you to know that equation. 1/2 times the capacitance, which is in Faradays. So Faradays times, or farads, not Faradays, farads times volts squared gives you joules, or energy. We're not going to have time to get into voltage density. And I throw in some slides here that kind of go along with the book. All of these are in the book. So that kind of concludes everything that I wanted you to know from this chapter. I've given you some homework assignments in here. And what that means is if you do those, actually, I don't know what happened. There should have been, on these blank pages, there should be ones. But I'll include answers to those questions in the course notes to help you kind of understand how to do problems associated with this knowledge. And I always recommend, I mean, I haven't been verbally saying it, but I should. Look over those problems and see if you can figure them out. I give you those answers to help you so that when the test comes, you know how to do the problems. That's it for now. If you have any questions, let me know.